In this video, we will discuss about the PN junction, which is main part of the semiconductors. So before coming on to the PN junction, I'll give a brief introduction of what is semiconductor and what are the P-type semiconductors and N-type semiconductors before coming on to the PN junction. So why there is the advantage of the semiconductors are that they need simple excitation like light or small applied voltage for the carriers to flow. What used to happen earlier is, if you would have seen the old televisions, they were very big boxes and having a lot of glass tubes which are diodes and triodes, and they actually needed a high voltage to get excitation before they discharge the electrons for the flow of the current. So all these things are being eliminated in the semiconductor, and the carriers flow even if in the solid state itself. So no vacuum is required. They are very small in size and they have a very high reliability as compared to the vacuum devices. So they are now used in the electronics industry. So what is a semiconductor? Semiconductor, as the name suggests, it is in between the insulators and the conductors. So their resistivity and the conductivity lies in between insulators and conductors. The semiconductors are basically all the fourth group electrons or four group elements of the periodic table comes in this category. Especially if I take the example of silicon and germanium, they are the semiconductors. So for the simplicity and not going into much detail, I have just made a crystal lattice of a germanium, where each atoms are arranged as you can see in this screen, and each one is having the four electrons in the outer shell. So this is the lattice. So what happens when the temperature increases? They are connected with a covalent bond. So when the increase in the temperature, the thermal energy of the electrons increased, and they break the covalent bond to conduct the electricity. So these are called as the intrinsic semiconductors. They are pure semiconductors. But to increase their conductivity, we add a simple small amount of impurity, which is called as the dopant into it, and it becomes an extrinsic semiconductor. So what is extrinsic semiconductor? These are obtained by adding or doping pure semiconductors with the impurity atoms having valency different from the host atoms. So semiconductors, as I told, they have a valency 4, they have 4 electrons in the outer shell, whereas the impurity which is generally added into them has a valency 3 or 5, that is plus 1 or minus, which either adds to the free electrons or to the holes, making them N-type and P-type semiconductors, which is explained below. The requirement of the dopants, it should replace the semiconductor atom in such a way so that there is no damage to the actual crystal lattice of the semiconductors. So these extrinsic semiconductors, as I told, depending on the dopant, are of two types: N-type semiconductors and P-type semiconductors. In an N-type semiconductor, a pentavalent impurity is being added. You can see here in this figure, I have neatly replaced the germanium, one of the germanium atoms, the arsenic atoms, which has 5 electrons in its outermost orbit, and pentavalent impurity is added. So what is happening? There is an extra free electron, which is an unbounded free electrons, which is responsible for the to conduct the current or to conduct the electricity. So the electrons becomes the major charge carriers in an N-type semiconductor. Since arsenic is actually losing one of the electrons, so it becomes positively charged, and we call as a donor atom. We call as a donor atom. The schematic representation you can see is here. It is like this. You have a positive donor atoms and there are free electrons around it. So you must remember what is the schematic representation of a N-type semiconductor. Hope you would have understood. I will come to the P-type semiconductor. P-type semiconductor comes with a tetravalent impurity. Here I have replaced one of the germanium atom with the aluminium, which has 3 atoms in its 3 electrons in its outermost orbit, and there is a hole. And with the increase in the temperature, the hole moves from one atom to another, and the electrons is replaced by holes. So aluminium becomes, because an electron is added, it becomes negatively charged. It becomes negatively. So we call it as an acceptor. We call it an acceptor atoms. And since holes are moving, so holes becomes the majority charge carriers, and which are positively charged. So we call it as a p-type semiconductor. The schematic represent is this. See, all the minus ions which I have shown is an acceptor impurity. Acceptor impurity atoms are there, and the holes are the majority charge carriers. So this is a p-type semiconductor. Now we come to the p-n junction. p-n junction, I hope you would have understood now what is n-type and p-type semiconductor. For a revision, n-type semiconductors have electrons as the majority charge carriers, and positive, and the positive donors, you can see here there are positive donors because they give rise to, they increases the number of electrons. And in the p-type semiconductors, you have an acceptor impurity which is negatively charged, and the holes are the majority charge carriers. Now in a p-n junction, it is a single crystal in which semiconductors are doped in such a fashion so that half of it becomes a p-type conductor and p-type semiconductor, and half of it becomes the n-type semiconductors. So there is a junction which gets created. This is called as a p-n junction. What happens at the p-n junction is, since you can see the holes in this, the holes are the majority charge carriers. These are the holes which are the majority charge carriers, and here electrons are the majority charge carriers in n-type. And in this region, because it's a junction, so what happens, the holes are positive charge and the negative charge, they combine. And so because of the acceptor ions which is on the p side, and because of the donor ions which are on the n side, so now you see that recombination happens at the junction. So this is called as a junction. This is called as a junction. And this layer, this is called as the depletion layer. We call it as a depletion layer. What happens here? Because the holes which are present here, I am seeing the holes here, and there are the electrons. There are the electrons which are on this side. So they combine with each other. They combine with each other, and they get eliminated. So here you can see there is a layer of acceptor ion and acceptor atoms, and there is a layer of donor atoms on the other side. So this makes this side as positive and the p side as a negative side. So this gives rise to a potential which we called as a VB. We called as a VB. Why we are suggesting a name VB? Because this is called as a barrier potential. Barrier potential. This recombination, what we have shown here, it doesn't happen indefinitely. Up to certain stage, this happens, and when this barrier voltage, because the barrier voltage is created, so when this voltage is created, barrier voltage, it does not allow, it does not allow the holes to go on this side, and it does not allow the electrons to come to this side. Okay, so this stops, this barrier voltage, it stops the movement of the majority carriers in the p-n junction. In the p p-type semiconductor, I will write p-type semiconductor, and here n-type semiconductor. Okay, because of this barrier, you can see it's a positive charge. It's a positive charge, so it will not allow any positive charge. It will repel it to this side. Similarly, this electron is coming. It comes because of the positive, but because of the potential which is developed, as per the, because of this layer, it will not, it will gets repelled. So it does not allow the majority carriers to come to the p side. So this is called as a barrier potential. So because of this, there is an electric field. There is an electric field EB. Of course, it will get created, and that is from the positive side to the negative side. And this EB is actually given by VB upon D, where D is called as the width of the. This is called as the width of the depletion layer. Depletion layer. Hmm? Now, when we apply a positive voltage, or when we apply a positive voltage to the P side and a negative voltage on a battery like this, such that the P type is positive, P semiconductor is positive and N side is negative, what happens? It will create an electric field. It will create an electric field and making holes to move to this side. So holes starts moving to this side, holes starts moving to this side, and similarly, because of the electric field, electrons starts moving to this side. Now, as long as this V, as long as this V is less than barrier potential, so they do not get enough energy. These will not get enough energy. This will not get enough energy to cross this. They will not get enough energy to cross this. Even this will also not get enough energy to cross this. So the crossing is not happening. So current is not flowing through it. But when V is greater than VB, what happens? The energy which is acquired by them, or the force which it exerts, it becomes so large that it crosses and goes towards this side. Similarly, electrons cross and comes to this side. So all this movement starts happening and gives rise to the current. So in a PN junction, whenever V is greater than VB, the current starts flowing, and we see that it is forward biased. It is forward biased. It is forward biased. And when we do it, I will now just draw simple like that. This is P and this is N type. And if I make it negatively charged, P side is negatively charged and V is positively charged, and this is a VB potential. As you know, it is in this direction. So this potential adds to the barrier potential. The applied potential, applied potential adds to the barrier potential. So the depletion layer increases. Depletion layer increases because there is a further increase in the barrier voltage. There is a further increase in the barrier voltage. So net potential becomes V plus VB, means barrier further increases and no movement of majority carriers happens in this case. So we say that in this case junction is reverse biased. This is reverse biased. And this is the principle behind the flow of the current when a junction is forward biased and stop of the current or no flow of the current when it is reversed biased. So these are the principles which is being adopted for the diodes. So we will cover more about diodes and then later on transistors in our next video. Thank you.